Thank you very much, Amit. I'm excited to be here. A quick word, so thanks for that great introduction. A quick word about myself. I've been at Intel. I'm a long-time diehard Intel person working in the software tools space for a long time. And what I would like to talk today about is how Intel software, developer software, has been evolving over our long history of software tools. So without further ado, let's dive right into it. So we really got started in the software tooling space in the 80s and perhaps even earlier, right? This is the earliest record we could find. I was certainly not here at that time. And some of our first work was in the compiler space, Fortran compilers, Fortran and C compilers, and debuggers. Right? This was the era of new architecture, a lot of innovation in architectures and so on. And everybody had their own proprietary compilers, proprietary front ends, IRs, and compilers were an area of differentiation in addition to the architecture. And as we progressed through the 80s, we came into the 90s, C++ became popular, C front-based compilers, and then eventually in the 2000s, Edison Design Group-based C++ compilers. So again, those were the basis of some of our early compiler work. Scientific libraries were common with everybody. So we had our own math kernel and integrated performance primitive libraries. And vTune was an early visual performance debugging aid that was used, that was very, very popular amongst gamers and people optimizing for our processors. All of that came in the 90s, and we were really proud of everything. You'll also see here a screenshot of a CD with all of those tools packaged together in what we called at the time Intel Software Development Products. Going forward into the 2000s, as architectures were hitting a power wall, parallelism was imminent, and Intel went on a software acquisition spree, getting a number of companies that focused on parallel computing. Right, so in 2000, they purchased this company called Cook & Associates that had a really great C++ compiler and really one of the first OpenMP implementations in the world for Fortran and C++. I happened to be part of that acquisition. Later in, I think, 2001 timeframe, we acquired the compact Fortran compiler as Intel was starting to get bigger into HPC with Beowulf clusters, et cetera. Some of the technology that was acquired, eventually became Thread Checker and Inspector, and Intel launched first package of tools called threading tools. We also acquired this company in Germany called Palace that offered Vampire and Vampire Trace, which were MPI analysis tools, trace analysis tools. And they also had their own MPI library. We formed a team with them, and that was the basis of starting our Intel MPI library project, which I hope many of you know about. Through the 2000s, right, as parallelism was taking off, we looked at the shortcomings of existing parallel programming models and invented this thing called threading building blocks, for which the key developers just launched a brand new book called Today's TBB just last week. So 3 different books published on that, started around 2006, 2007 timeframe, and going very strong today. The key issues it was addressing was, OpenMP was limited to assume you could take over the whole machine. This was much more forgiving to multiple teams of threads working together. We were also getting big into gaming as graphics were taking off. And so we had this graphics performance analyzers that are really focused for gamers. The first formal toolkit was released, Intel Cluster Toolkit, also in this time frame. And then we also acquired Silkarts and RapidMind. And with those, we fielded a Silk compiler and this array building blocks library. Now, it turns out some of this technology didn't survive, although many people from those acquisitions still are with Intel and contributing. Again, the technology has survived into our products. Maybe the products as described didn't survive exactly. And finally, IXPUG is named after Intel Xeon Phi, right? So early on, IXPUG stood for Intel Xeon Phi Users Group. That was part of Intel's entry into accelerators, which has been a slow going for us. We're still finally fielding GPUs. We started with this huge array of of CPUs called Xeon Phi. In the early 2000s, as machine learning and analytics were taking off, we started this data analytics library, which continues to this day. And we really took all our libraries and fielded them to customers in the form of hooking them up with Python interfaces and making it broadly available to Python, just as Python was starting to take off. In the late 2010s, AI and deep learning were taking off. And so we fielded our versions of deep neural network library, initially for our CPUs, and then over time for our GPUs also. This was also the time when we launched Open Fabrics interface. You could say the work for that started in the 2013, 2014 timeframe. The first version was released in 2016. And what that does is abstracts different network fabrics so that our MPI could easily switch dynamically between different network fabrics and use them all simultaneously also. And again, for deep learning, we also launched our collective communications library, which initially was called MLSL, Machine Learning Scaling Library, that we eventually renamed to Collective Communications Library. So you can see we have a rich history of what we've done. And as we were bringing GPUs to market, we saw this need for a better and open programming model for GPUs. And that's where OneAPI was born. OneAPI is a set of specifications that are based on the SYCL language. SYCL is a Kronos language standard, and that's what we adopted. We also acquired CodePlay. CodePlay is one of the pioneers of SYCL. And today they help us build all parts of our software stack, OneAPI software stack, as well as fielding a OneAPI implementation for NVIDIA and AMD. And what we've been doing lately is launching new features such as SYCL Graph and Joint Matrix, which we'll describe in a little bit and in the rest of the day. And finally, we also launched our own SHMEM earlier last year. So SYCL has evolved into, well, Intel launched it as OneAPI, and it has evolved into this UXL Foundation, which is a sub-foundation of the Linux Foundation. So what I want to do next is talk a little bit about what we've been working on over the last 5 years. And our focus really has been on improving our foundational technology. For compilers, as I described, in the early 80s and 90s, everybody had their own proprietary front end, their own proprietary IR, and their own proprietary backends. What's happened over time, in the 90s and 2000s, for C++, everybody started converging around C front first as a design group, and then later on around Clang as the C++ front end. So that's standard for everybody. In addition, compiler technology became more commonplace. So this LLVM project out of the University of Illinois became a very popular compiler infrastructure, which we've adopted across all our compilers now. The other thing that has enabled us to add is these sanitizers that do various kinds of checkings. We'll talk more about that in a little bit. In terms of programming models, OpenMP has been around since the late 90s. We've been enhancing it, adding 4 GPUs, adding offload support, and we've been taking threading building blocks, did a complete rewrite of that also in the 2019-2020 timeframe. Made it C++, made it more modern, removed some of the older features that made the language clunky. And so that's going strong. And finally, all our libraries, we added SYCL interfaces to them so you can easily run them on GPUs. For distributed programming, what we've been doing is to our MPI, we've been adding GPU-initiated communication. We've been adding, enhancing our fabric support, adding more fabrics, continuing to enhance kind of collective communications, and added SHMEM, as I mentioned earlier. In the analyzer space, right, we had, again, part of our early technology acquisitions, we had this product called Advisor, which we've grown into, early on in the 2000s. It was focused on adding parallelism into your applications. So it was based on Threading Advisor. And over time, we added memory analysis capabilities to it. And then we added vectorization analysis capabilities to it, and then offload analysis capability to it, including roofline analysis. So Advisor is a product that has grown from technology we had acquired, and then really built upon strongly. Inspector, similarly, was proprietary, but as this technology is becoming broadly available in LLVM, we have shifted to using the LLVM sanitizers, which offer much better support for everybody. vTune itself, I touched upon earlier, one of the earliest visual performance analysis tools, and has evolved from CPU-only analysis to whole system analysis. And we've really added this client-server model so your install footprint can be small and you can get working very, very quickly. So that's what we've been focusing on, and a little bit deeper look at compilers and what we've been doing with LLVM. So one of the benefits of adopting LLVM is just faster compile speeds. And you can see here for Fortran, our new IFX compiler is about 18% faster than iFort compilers. Now, as you well understand, for a developer, a fast compile debug edit cycle is really critical, and this really enables that. Similarly for C++, 16% better speed over our older compilers, ICC. The other thing, as the whole world converges around Clang, error messages become easier. Everybody gets trained to the error messages. That combined with Clang just doing a much better, with a new implementation of the front end, doing a much better job of error messages, much better performance reports and optimization reports. And as I mentioned earlier, a lot of different sanitizers to help you check that your code is correct. You can also leverage optimizations that are coming from the LLVM community. You can contribute what you have there. We've been really communicating in the vectorization and loop transformation phase. Accelerator support, OpenMP offload for GPUs is, we started OpenMP offload in LLVM. We also really introduced our OpenMP into LLVM earlier. And now we're proud to join this offload project for OpenMP offload and also for SYCL offload. We're in the process of upstreaming SYCL for CPU and GPU, so that's something that that is in flight, and would love your contributions in that space. And finally, what LLVM enables is many other languages besides Fortran and C++, and really drives open standards. We can engage much better with the community. We can benefit from them. They can benefit from our contributions. So that's going very well. It's adopted by everybody, so it's much easier for users to understand the same set of tools. And the licensing for LLVM is very friendly, so we can feel our own compilers as we see benefit. Going forward, a quick look at our new C++ and Fortran compilers, again, completely LLVM based. We have launched both of these. C++ was launched 2 or 3 years ago, 3 or 4 years ago. And Fortran was launched in the last couple of years. At this point, we have switched to these completely, although we do make older compilers available for customers if they need them. And what you'll see is we're able to get much better performance out of our LLVM compilers compared to the competition. And as I mentioned, all of our work can easily be leveraged by other languages. For example, MLIR is a compiler infrastructure for building other IRs. Our work can be leveraged in there. OpenCL, Rust, Julia, Java, as part of the Tornado project, again, can leverage the work that's happening there. And collaboration with the community on the vectorizer and loop transformation continues, and other scalar transformations as well. So big benefit to users and to the whole community. Talking about sanitizers, so this is part of our inspector effort has migrated into LLVM sanitizers. These are supported by a much broader community, and there wasn't a whole lot of value in until continuing a proprietary tool when everybody's used to these tools that are available in LLVM. So at this point, we've got all 6 of these sanitizers enabled for our C++ compilers on CPU. The first 3 of these are also available for Fortran on the CPU. The first 2 for our GPUs in C++, and the first one address sanitizer Fortran on our GPUs as well. So what each of these does is address sanitizers, again, find and fix memory-related errors, use after free, etc. Memory sanitizer, uninitialized memory, leak sanitizer, memory leaks, undefined behavior, data races, deadlocks, and just numerical precision related errors. OpenMP is another area we have been working on a lot, and we've been enabling it for GPUs. So we were some of the early pioneers of OpenMP. A lot of LLVM's OpenMP support is based on work we've contributed to the community. And really, OpenMP runs from your laptop to your supercomputers, right? It's everywhere. After, I think the first specification was launched in the late 90s. So at this point, almost 30 years old, available everywhere. We've been working with the LLVM community on liboffload to enable better standard offload support for the whole ecosystem. In terms of our implementation, version 5.x is fully supported. We've got all the tools and debugging for it, as well as memory management and tasking features. Version 6.0, we've just started support. About a third of that is complete, and you can get much better accelerator support with OpenMP 6.0, competing with OpenACC. And finally, OpenMP, for those who don't know, is the foundation for AI on the CPU. So if you're familiar with the PyTorch stack, right, PyTorch has these operators in this C++ template library called A10. Underneath A10 sits, for the CPU, sits an OpenMP backend that can use all the CPU cores, etc. If you're interested in more, I encourage you to visit Young Nim and Yiluo's talk at noon Central Time later today. So what we're going to do is sort of look at our last 5 years and a little bit of motivation for them. If you look at the picture on the left, it describes where Intel is investing our die area, right? It's the number of transistors going into CPU cores in the dark blue, and accelerator cores, GPU and NPU, in the light blue. And you can see that we were at around 15% in 2010 for the accelerator core, to at this point about 45% or so. Out of that 45, really less than 10% is NPU. Most of that is GPU. This is on the client side. You can see where we're investing our technology, our transistor technology. On the right-hand side, where you are investing your operational dollars. But if you look at how much money is, how much power is consumed by the CPU subsystem on a server and the GPU subsystem in a server, you can see that GPUs were consuming about 5 to 7% in 2010 to more than half at this point. The top part of that is white, about 15% or so, has been relatively constant for peripherals like memory, disk, etc. By the way, these graphs are produced by Claude, getting data out of Claude. The key thing here is you can see where Intel is investing our transistor technology, where you're investing your operational dollars. And so from a programming perspective, as programmers, we need to be able to utilize these accelerators really well. That sort of motivates and explains why we're growing in the accelerator space. Now, the big problem in accelerators on the server side for compute specifically is that the programming model today is proprietary and locks you in. We have a number of customers who come to us with CUDA codes and say, hey, I would like to try your GPUs, but I cannot because I've got this thing, and can you help us? So that's one thing. The other thing, again, just as we had an explosion of architecture, CPU architectures in the 80s and 90s, we have an explosion of accelerator architectures in the last 5 years, and really to some extent even now. And what we find is, according to this survey from Evans Data Corporation, 48% of developers target systems that use more than one kind of processor or core. So for a developer, your challenges are, when each of these has a different programming model, how do you address them all? How do you flexibly switch between what works best for you? How you can integrate these different technologies together? And it really makes it much harder for you to write your software and be able to easily retarget it from one to another as the strengths change over time. So we were looking at that and we decided really what is missing in this world is an open software platform. And our goal here is to really unify the compute accelerator ecosystem around open standards. So SYCL, as we mentioned, is a Chronos language standard, started in 2014. It was a C++-based language for open portability for GPUs. Initially, it was a layer on top of OpenCL, and over time, it has grown beyond that. So in 2019, we announced this One API effort, which was initially a code name, but eventually became our brand name. And we rebranded all of our tools to this. But the vision behind One API was that you should be able to take one programming model and run it across different accelerators, including CPUs. The little things on the right of that One API logo, one DPL, one DNN, one CCL, et cetera, are different library interfaces that offer different library APIs that offer SYCL interfaces so that you can easily target different accelerators with fixed function libraries. We launched the first version of One API in 2020, and that has been going strong. It wasn't an Intel-only thing initially. I think we got feedback from customers. We wanted to see more implementations of that on more than Intel GPUs, so we enabled that. And we took all that work and donated it to the Linux Foundation to start this UXL, Unified Acceleration Foundation, with open industry governance. So we did that in 23. We'll talk about what UXL is about. So it's under the Linux Foundation's Joint Development Foundation. It is openly governed by multiple steering members. You can see all equal members there, a long list of ARM, Broadcom, Fujitsu, GE Healthcare, Intel, Google Cloud, Samsung, Qualcomm, and Imagination Technologies. We have a few general members and a lot of contributing members also. So contributing members can join for free and contribute to all the technical discussions in the working groups and the special interest groups. General members get to vote on different things, but overall, this ratification of the specifications is limited to the steering members. Our goal here is broad-based industry participation and adoption. And contributions, which we're seeing from all the steering members today. You can see the structure of UXL, and you'll see at the bottom of this are the specifications, which happen to be called the One API specifications. Now, I wish they would rename the specifications to something different, because One API, Intel happens to have branded our products as One API products also. So if you look at this pictorially, UXL is defining the accelerated computing standards on the left-hand side. A number of people doing that with equal votes. They're driving not only the specifications forward, but also an open source implementation forward. And the UXL Foundation is really working to make sure there are builds available for multiple different architectures of the open source projects that are part of UXL. What it does, again, it's an open industry specification. There's freedom for you in choosing your hardware with a single model. The goal here is performance, portability, and productivity. And it's really driven by the community. Now, Intel, as I mentioned, we've branded our products One API. And the thing that's common to the left-hand side and right-hand side here is the One API specifications. So Intel's One API implementation is optimized for our hardware, proven performance, with really good capabilities, supports Fortran, Python built on top of an API, OpenMP and MPI. And all of our tools as of a few years ago, I think around 2020 timeframe, are available for free. But we also offer commercial support for customers that need it and that need much faster handholding and so on. You can see in the middle, all the different products that we support, all the domains, et cetera. Going forward, so what we've been focusing on is implementing SYCL. So as I mentioned, it's an open standard from Chronos Group, started in 2014. Now we undertook a major change in 2020 that was called the SYCL 2020 standard. As we adopted this in late 18, early 19 and announced it, we made a number of improvements to SYCL that made it really an industrial strength standard. just driven by multiple vendors and users. The other thing that we've added is an ability to extend SYCL so that you can get hardware-specific performance if you need to. Although the intention, of course, is that the general SYCL model is also available and is performant across a broad range of hardware. Interoperability with other programming models was also added. And Intel's implementation of SYCL is called the Intel DPC++/C++ compiler. SYCL 2020 has a large conformance suite, and we're also proud to have the first SYCL 2020 compliant implementation already. It's based on modern C++, and you can see everything that it does on the right-hand side there. So in addition to implementing SYCL implementations, that's our job. Your job as users is to create SYCL applications. You can do that in two ways. You can write from scratch or port from CUDA. The intention is that you end up with a single code base that can run on accelerators from multiple vendors. We've got this tool, compiler-based tool called Cyclomatic that we have open sourced as of a couple of years ago, which aids in migrating from CUDA code from CUDA applications. What we've found is for people not familiar with their code base, Cyclomatic is very good at automatically handling large chunks of your CUDA applications. We've seen applications, pretty large applications that are fully handled by Cyclomatic, so you need to do very little. In general, we say it'll handle 90 to 95% of your application. It will leave code behind. It's a source-to-source translator. It will leave comments behind in the generated SYCL code where it cannot handle something and leave you pointers about how you can go about addressing that. And what users have found is it is a really great learning aid. As you learn how to transition CUDA code to SYCL, you quickly get the hang of how to write SYCL code also. So that's one use case where you're not familiar with your code. The other use case we found is a lot of people who are experts in CUDA and completely understand your code. Again, SYCL is close enough to CUDA that they can just automatically pick it up and start to write directly in SYCL. So we've got both kinds of users, and Cyclomatic really serves as a great aid to learn how you transform your CUDA code to SYCL, where it has difficulty and how you can rewrite that. And our job, again, with those SYCL applications is to run them everywhere. So they run on all Intel CPUs and GPUs. They run on NVIDIA GPUs and Intel GPUs. And part of our motivation behind our CodePlay acquisition was to run SYCL and WinAPI on Intel and AMD, and that is available from CodePlay today as a plugin to the Intel-based toolkit. The other cool thing is that performance you get on the resultant SYCL, is comparable to CUDA. So the graph on the right-hand side, what it shows is if you take an original CUDA application, transform it with Cyclomatic, and then run it on the same NVIDIA GPU that you ran your original CUDA code on, you get more or less the same performance. And there are a couple of bars where the blue, which is the SYCL code, runs faster, and one bar where the green runs faster. I think those are just idiosyncrasies of different compilers. There is no fundamental reason because the programming models for CUDA and SYCL are the same. So users were initially surprised it could do that well, but when we explained that it's the same programming model, and ultimately our SYCL compiler generates PTX in the same way that the CUDA compiler does, you understand that it really should get the same performance on the same GPU. And we've got many applications and frameworks using SYCL available today. There's a SYCL catalog that's linked at the bottom of the slide. 40 plus applications, including some you might be familiar with. Argonne is using that as a big user, llama.cpp, Cutlass, which is a linear algebra library we'll talk about in a little bit, Cocos framework, and many others. My favorite here is really GrowMax. If you've had a chance to visit either ISC or SC in the last 1 or 2 years, you may have seen Eric demonstrating GrowMax running with SYCL on his system. What's cool about that is his system has 3 GPUs in it. It has an Intel GPU in it, an NVIDIA GPU in it, and an AMD GPU in it. And he runs the same application at the same time using all three GPUs, right? This shows the power of the heterogeneity of the SYCL programming model, that you can use three different GPUs from three different vendors and accelerate the same application onto those and load balance across those. Finally, continuing our SYCL everywhere mission, it's available from supercomputers to laptops, right? So as we were preparing for this talk, we took some applications from Aurora, which is the Argonne supercomputer, and we ran them on our laptops and on our discrete GPUs. And really, everything just ran out of the box. So GrowMax, so those are some examples of what we just took that was tuned for Aurora and simply ran it on our B series graphics card and our integrated GPUs. You can see this quote from Yellow. You will, if you go to the OpenMP talk later on, you can hear from him directly. But basically, he says he was able to run the same code on both Aurora and on his AI workstation, and found that really this makes it much easier to do a lot of your programming on your own laptop and desktop systems. So looking ahead, what's coming up? If you look at how floating point performance has been evolving, right, this shows amazing progress in FP32 flops and FP64 flops on a GPU. You can see from 2012 to 2024, about a 20 to 40x growth in FP32 flops and about similar growth in FP64 flops. Right? Pretty impressive. But if you fast forward, what you'll find is, notice the scale change. The top end of the scale was 160 previously, now it's 8,000. So about a 50x change in scale. And you see these lower precision hops start to appear, FP16, FP8, and FP04, growing at an absolute crazy exponential scale here. It's enabled by these high precision, low precision systolic units. So not super easy to program, but really an amazing power that is available in these things. So this kind of sets the stage for making all this hardware investment easily accessible to you, the programmer. So in this regard, we've got three solutions that we're doing and then looking at others also. And one is our math kernel library, offers mixed precision via alternate compute modes or iterative refinement. So you can give arguments or set environment variables about what characteristics you want, and then some routines in MKL have support for lower precision, where they can take your input and your precision, run in lower precision, and then give you answers based on the parameters you give it. Similarly, DNN, again, these lower precision hardware is built for neural networks. So certainly DNN has support for all the different data types, fast matrix multiply, etc. And finally, SYCL joint matrix offers a programming abstraction over these systolic units. So we've got one interface, really the only interface of its kind, that you can run on both CPUs and GPUs not just from Intel, but also from other vendors. So language extension for that. So first, Greg Henry is going to be talking later about using low precision. So it would be great to go listen to him. I think he's the next talk. And going forward, Dunya is going to be talking about SYCL joint matrix right after Greg. So what is it? It's a SYCL extension for matrix programming. It's part of our compilers, and you can check out the specification at that site. As I said, it is portable and performant way to access really the only interface that you can use both on the matrix units on our GPUs and the matrix units on our CPUs, in addition to the NVIDIA Tensor cores and the AMD matrix cores. The benefits should be obvious. Productivity, you only need to write once and tune the parameters for each kind of matrix hardware. But really your algorithms can be expressed once. It maps directly to lower level intrinsics and to the hardware. So you get top performance and you get the portability to write once and run everywhere with just parameter changes. Finally, Cutlass. Cutlass is a linear algebra building block that NVIDIA has open sourced and has become very popular in lots of different AI frameworks and other frameworks. Really, part of the libraries are also implemented with Cutlass. What we've done is we've taken Cutlass and created a SYCL-enabled backend for Cutlass. We're calling the project Cutlass SYCL. What Cutlass is a C++ template library as part of Cutlass 3.0. NVIDIA really re-architected that to make it very friendly to add different kinds of backends to that. And as part of Cutlass 4.0, they're really adding compiler technology with MLIR into Cutlass. So what we've done is taken Cutlass 3.0 and added our SYCL backend to that. And that is available in early form today. It is an open source project. And really we'd love it if you join us and help us enable, help us build a Cutlass for SYCL everywhere that is optimized for any kind of GPU that you're interested in. Again, Cutlass has got a lot of downloads used in multiple projects, including major DL frameworks like PyTorch, Llama.cpp, and SGLang. SYCL graph is another thing we're working on. So as we were working on our accelerator stack for Aurora, we found that kernels in HPC tend to be fairly large, whereas kernels in the AI space tend to be very small. So the overhead of kernel submission is critical, right? So we really need to optimize kernel latency, kernel submission latency. And what SYCL graph does is you can submit a graph of computation, you can capture how the graph is defined, and then you can only do one submission to capture that over and over and really greatly reduce the latency. So this turns out to be pretty popular, not only in AI frameworks, but also GROMACS uses this, and Cocos has the ability to use this also. So again, this is part of the Intel C++ compilers, and it's available in open source on GitHub. You can check out Pablo's talk this afternoon at 1:30. And finally, GPU initiated communication with the Intel MPI library. So Intel MPI library is a multi-fabric implementation, as I mentioned before, of MPI. We have dynamic selection of the optimal components, and we're compliant with MPI 4.0. What we've been adding is device-initiated communication. You can see that picture on the right. We've added this to our compilers, to our library, and we're in the process of submitting this to the next standard as a new extension to make it much easier to do this. So basically, you can trigger a data transfer from the device, and it's handled for scale up by the device itself. For scale out, the host handles it, but really the device just needs to initiate that. The MPI put notify. When the data transfer is complete by the host, that the target GPU is automatically notified. It really greatly simplifies how communication happens, and really helps you overlap communication and computation on the same side. Right? Previously, the device would have to check back and forth multiple times and couldn't carry on with its computation. It's already supported on both Intel and NVIDIA GPUs and RMPI. What I've tried to show you is Intel software development tools have a rich history of innovation. We've been doing this since the 80s. We've got an unbelievable set of components available. Many of you use them. What has been strong for us is that we're based on open standards. We've always preferred standards for this. And even when we were doing proprietary work, we do open source implementations and invite everybody to submit, to contribute to that and adopt it. And the goal here really is as programmers, you should have choice on where you run your applications. You shouldn't be locked into proprietary hardware and software. So please join us in creating an open GPU programming ecosystem. Many of you use our tools today. You'll be able to use the tools you know and love on today's integrated and discrete GPUs, from supercomputers to laptops. Thank you very much. I think we have time for a few questions.
Thanks, Dr. Shah, for the great presentation. And it's really inspiring to see the past and current roadmap of Intel software. So we have some time for questions. There are 7 questions on the Q&A. I would like to read them for you. So the
Okay.
first question is by George, and he says, many software firms are refactoring their code for optimized performance. Is the 18% faster because of the hardware or software improvements? Can you prove this? I think Steve has answered some part of it, and would you like to say something about that?
Absolutely. Yeah. This is really based on this is a software comparison on the same hardware. How Intel's compiler, or Intel's proprietary compiler. I think this was referring to the compile time speed improvements. How Intel's compiler, the new compiler, LLVM-based compiler,
Well, yeah.
yeah, it compares to the ICC compiler. So this is on the same hardware. This does not factor in hardware improvements.
Just to add that, I had a paper in IC high performance 2 years before, and we showed LLVM based Fortran compiler was performing 17% better over the traditional ones. And this was really great to see the good performance on Sapphire Rapids at least. Uh, so the next question is by Michael. Compared to the classic compilers, are there any features that LLVM-based compilers do not yet support?
We've tried to add everything. I think the area where we didn't have as many numerical precision controls as we launched our LLVM-based compiler. We've been adding them over time. So that's been one area. The second area really has been we had a really rich history of proprietary compilers, and there were many optimizations in there that were not present in LLVM compilers. So for the most part, right, if you ran a modern application, you got very good performance, but there were a few cases where we found that our older compilers performed better, and we've been slowly adding those into our LLVM-based compilers as well. From a feature perspective, we find that the LLVM community, adopts C++ standards quickly, is working on a Fortran compiler also. We'll see how that evolves. And yeah, we're eager to see how that evolves and whether we can contribute to that or not.
So I recently attended a conference by UCAR, the US Climate and Atmospheric Research, and Damien from Berkeley, he was presenting. And he told us that since the adaptation of LLVM, he before that he was filing like one bug every week to the Fortran community, but with the LLVM, I think his bug submission has reduced almost to zero. Like he's so glad with the LLVM adaptation that bugs have reduced significantly.
Yeah, that's great to hear. Thank you.
Mhm. Mhm. And the next question is by Andre. He's saying SQL itself is a portable standard, and one API aims for portability. Yet many view it as Intel-only things. Example, Cocos use SQL only for Intel GPUs and primarily relies on CUDA or heap for other hardware. Are there any plans to better promote specifically the portability aspect of SQL or one API? Maybe inviting other GPU vendors through UXL or making SQL one API omnipresent, which are available on almost any Linux machines via Mesa.
Yeah, this is a good question, right? I think both AMD and NVIDIA are welcome to join UXL. We're not excluding them at all. So, and again, based on ask from users, we made one API compilers available on NVIDIA and AMD. It's an open source project, right? As the community sees interest in this and sees value of this, we really welcome contribution from the community, right? That's what ultimately is needed, right? So there's a great parallel here to the late 80s, early 90s, 2000s, right? There was a proliferation of shared memory programming languages at that time, right? Everybody had their own directives. And ultimately, the user community came together and demanded a standardization. And that's sort of the beginning of how OpenMP came about. And again, early on in the life of a technology, it makes sense for people to experiment and figure out the best way to do things. But after some maturation, it becomes obvious the best way to program these different accelerators. And I think that has been proven today. And that is what we intend to do here. we welcome contributions for others, really. I think the open source, the other thing that LLVM has taught us is you don't actually need a vendor support to build a fantastic compiler. And that's what we've done with SYCL on AMD and SYCL on NVIDIA. So again, it doesn't, a few university students, a few researchers, a few labs get together and make that standard is what's needed to really drive it forward. We can only do so much on our own.
Thank you. The next question is by Michael. He's asking, how do SYCL and OpenMP GPU offloading compare in terms of performance? If we write relatively well-coded SYCL and OMP offloading codes, are there any cases where one dominates over the other?
That is not our intention. They should work the same, and underlying software stack is the same. Again, the great benefit of LLVM again is after a certain phase of the compiler, the underlying stack is the same, the optimizers are the same, the runtime system is the same. And I think as we showed sort of in the CUDA to SYCL example, right? If you code your algorithm the same way and the programming model is the same, then you get the same performance. So, and by the same token, right? If you're coding the same algorithm in OpenMP and SYCL, using the same software stack, you should see very similar performance.
But it's more portable and user productive, right? In terms of SYCL.
For C++ programmer, SYCL is much friendlier than OpenMP, although OpenMP certainly works super well for Fortran. So really OpenMP's strength is Fortran. It works well with C++ also, don't get me wrong, at all. It works very well with C++, but in some sense, SYCL is based on C++, so it's really very tightly integrated into the language, etc.
The next question is by Victor, and he says quite a few of our users use Cocos as portable CPU/GPU abstraction layer. And I personally find Cocos easier to write than SYCL. Does UXL intend to include Cocos?
Good question. So first, Cocos has a SYCL backend already. Second, I think Cocos is part of, there's another Linux Foundation project. Its name is escaping me right now. But there is another Linux Foundation project. I think SPAC is part of that project. Cocos is part of that project where they're trying to standardize around these things. So it is already a Linux Foundation project. There's already a SYCL backend for Cocos. And yeah, abstractions are really great for programmers, right? You want to avoid getting locked into a programming model. So Cocos has done a great job of that.
Okay. The next question is by George. Please forgive me for this question. What is an AI compiler? Doesn't it require a GPU, or it's applied to NPU or an accelerator? I don't know which slide he's mentioning.
And yeah,
AI compiler. Yeah.
AI compiler. So I'll give one example. Triton is a language. Don't get confused with NVIDIA's Triton inference framework. But this is OpenAI's Triton language. It is a Pythonic domain-specific language that's built for tensor programming. So an AI compiler takes a domain-specific language and generates AI code for that. So that's one example. Again, there's a lot of MLIR-based work that's happening with tiled languages and tiled IRs. And in general, an AI compiler is taking your code and targeting an AI processor, a systolic unit, or a GPU, something like that. So that's what we meant.
Victor asked a history question. Remind me of what KUCK vectorization tool was called again. VAST, something like that?
No, the Cook tool was called CAP, KAP. VAST was from Pacific Sierra Research. John Lamec's company.
Okay. Does SYCL receive ideas from C++ parallel standard or vice versa? Has SYCL contributed back to C++ parallel?
Yes, this is an we absolutely are interested in getting more and more features of SYCL into C++. What we've been focusing on is enhancing the parallel capabilities of STL. So parallel STL work in C++, a lot of that originated at Intel. We've donated that to the C++ standards body. We're continually adding more capabilities there, better vectorization support, better executor support, and so on. So that's an active area of work. I think full SYCL is early, what we want to, but that is a path that we're certainly pursuing today.
Okay. Yeah, so I think you have answered all the questions. There are no more questions I see. We can wait for a couple of seconds to see if some questions pops up. Apart from that, I had a question regarding the MPI. So do you have plans to add the latest 4.1 standard, or the MPI forum is moving to the 5.0 standard roadmap in a couple of months, but there are some recent additions to the MPI. So what are your plans to how do you want to go with the latest additions?
I think we're working on them, and yeah, we intend to bring them out. I don't have a timeline that I can share, but certainly the 4.1 work and the 5.0 work. Somebody reminds me, the software foundation that Cocos is a part of is called the High Performance Software Foundation. That SPAC and Cocos and a number of other projects are part of.
There was a slide number 18. So which NVIDIA GPU did you compare in that?
I think that was on an A100. I'm assuming that was SYCL performance on NVIDIA GPUs compared to CUDA. That was an A100 GPU, although we expect the same, for those applications, the same kind of performance on any GPUs.
Yeah, I have seen some slides from Argonne National Lab showing a better performance or equal performance with the 800 GPUs. Yeah, that's what I was thinking of. Yeah.
Yeah.
Thanks.
Although that particular slide was, again, not comparing an Intel GPU to an NVIDIA GPU. It was simply comparing CUDA, an NVIDIA GPU, to SYCL on the same NVIDIA GPU, and that was an A100. But yes, I think Argonne is publishing data showing performance of PVC, their machine, against A100 and H100.
Thank you. Are there any questions, or someone wants to raise their hands so that I can make them speak? I don't see anyone raising their hands or asking the questions.
All right, so what I want to welcome everybody to really is to come contribute to this open ecosystem, right? It's working, it's fantastic. It is already available on our client GPUs, on our gaming GPUs, Battlemage, which are available for very economic price, and available on supercomputers like PVC. And we're continuing to build out our GPU hardware roadmap. But in the meantime, you can use that everywhere, including on your CPUs. But what really interesting is getting students to start contributing and really growing this open software ecosystem so that we're not locked into proprietary hardware, and we can really run our applications everywhere that we need.
Great. Thanks, Mr. Shah. So I think the next, I really am grateful for you to be our keynote speaker. And it was really inspiring to see, and motivates me to use more Intel technologies in our evaluations as well as the application runs. And I think there is an MD talk in the afternoon where David Hardy from University of Illinois, Urbana-Champaign will present some great numbers. So I'm excited to see his presentations. And yeah, thank you. Thanks for being here.
Thank you very much. I appreciate my honor.